So now we consider the multi-loop circuit, which is like the resistance in parallel. Resistance in parallel. So as you can see here, we have a battery E, we have R1, R2, R3 all in parallel. So in that case, if we try to substitute this part into the equivalent circuit, it is like here we have point A, we have point B, and then we may use a block, we may use a box to say it is like a black box, and then we exchange it to another element. So in such a case, if we cannot distinguish whether it is this one and this one, then we'll say this R eq is equivalent to these parts. Equivalent means we have the same current and the same voltage for different value of I and V, and then they will have the same pair, then we'll say it is equivalent circuit. So in this case, we can actually consider the KCL at this loop, So, so we'll consider there will be current I going through this battery, although we don't really know what I is if we consider this part independently. So in this case, we will have I1, I2, I3 going through R1, R2, R3 respectively. And then, of course, I will going through the whole REQ. So in this case, we will have E equals I REQ for this equivalent circuit. And for this one, as much as we know that I should be equal to I1 plus I2 plus I3 due to the KCL. So we have I equals I1 plus I2 plus I3. So we use KCL to get this one. So we know that I1, I2, I3, which is the current going through R1, R2, R3. So that we can use Ohm's law to link between the current and voltage of these three elements. So which is like I1 is actually E of V over R1, V over R1 plus V over R2. So we'll say this is V. This is also V. So this is V over I1, V over I2, V over I3. So we add all of them together, which is the I1 plus I2 plus I3. So in that case, or we can say it is V equals I REQ. So actually, we can slightly rearrange the term so that in this case, we will have V equals I times 1 over R1 plus 1 over R2 plus 1 over R3. And in that case, we know that REQ should be equal to this whole term, which means that we can also have a 1 over REQ equals to 1 over R1 plus 1 over R2 plus 1 over R3, which is the parallel resistance, So resistance in parallel, or parallel resistance. Okay, if we have n resistor in parallel, we can just take the inverse, take the reciprocal of all the resistance and add them together, and then take the reciprocal again. So it will be the parallel resistance. So it is easy. And up till now, you have learned the resistance and capacitance, the series parallel. So for series resistance, we add all of them together. But for parallel capacitance, we add all the capacitance together. And for parallel resistance, we take the reciprocal of the resistance, add them together, and take the reciprocal again to be the parallel resistance. And for series capacitance, we do the same thing, like the parallel resistance. So it is somehow the other way around. So we have series resistance. The calculation is like the parallel capacitance. And if we calculate the parallel resistance, it is like the series capacitance. So if you really consider the inductor, in chapter 30, I don't think we mentioned about how to calculate the series inductor, series inductance, or series inductor, or parallel inductor. So if we really calculate the series or parallel inductor, it is like the resistor. So if we have series inductor, it should be like L. It should be L EQ should be the sum of L J equals 1 to N. And for parallel, it should be like 1 over L EQ equals summation J from 1 to N, 1 over L J, like this. So when you calculate the series of parallel inductor, it should be like how we calculate the resistance, but it is the other way around with the capacitance. Okay, so next, we have a sample problem. Okay, so this one is like, so the figure A shows a multi-loop circuit containing one ideal battery and 4 resistance with the following value: 20 ohm, 20 ohm, 12 volt, 13 ohm, 8 ohm. What is the current through the battery? What is the current going through the battery? So in this case, as I mentioned before, we cannot really calculate the current going through the battery directly. We need to solve the whole circuit, and then we refer back to here, and then we can see the current going through the battery. Actually, the current going through the battery is actually the same as the battery going through R1 or R4, which is like, this is I, this is I, this is I. We like to consider, but at first glance, we cannot solve it directly, but it is not so difficult, I think. Yeah, so as you can see here, we have point B here, point C here. So R2 and R3 are in parallel. So we can calculate that R2 parallel R3 is actually 1 over, or actually, yeah, actually 1 over R2 plus 1 over R3, yeah, something like this. Or for two parallel resistance, you can actually remember this equation. It is easy to remember. I suppose you should have learned it in high school. So it is like 20 times 30 over 20 plus 30. So this is 600 over 50, which is 12 ohm. And we can simply observe that if we have series resistance, then the series resistance is like we add some positive value together. So series resistance will be larger than the original resistance. And for parallel resistance, then for maybe like if we have two resistors in parallel, then the parallel resistance will be smaller than the original two, or at least smaller than, yeah, or we can say smaller than the smaller resistor. So we have 12 ohm after parallel. So one specific case is if you have two resistance with the same value in parallel, it will be like R over 2. It will be like R over 2. If maybe like if R1 in parallel with R2 and R2 tends to infinity, then it will be like R1. yeah, so yes, this is the parallel resistance. So after the parallel resistance, it will be like we have a E here, and then we have R1, and then we still have R4 here, and then this one is R2 parallel R3. Okay, R4. So like this. So in this case, we can calculate I. Now, so I is E over R1 plus R2 parallel R3 plus R4, because R1 and this one and R4 are in series. So we just add all of them together, will be the equivalent resistance. So yeah, so this is, so now we can substitute the number. E is 12 volts, R is 20 ohm, and then this is 12, and this is 8. So this is 20, 40. So it is like 0.38, 0.38 for part A. Okay, so for part B, what is the current? I2 through R2, I2 through R2. So just now we know that I, this is I, this is I, this is I. Okay, so, but just now we have this equivalent circuit, and actually we of course can restore it to the original case. So in that case, we can really calculate what is the current going through R2. So as much as we know, I is 0.38. This is what we have found in part A. Okay, so we know R2 parallel R3. R2 parallel R3 is 12 ohm. It's 12 ohm. Just we also calculate this. So VBC will be nothing but I times R2 parallel R3, which is 0.3 times 12, which is 3.6 volt. 3.6 volt. Or you're going back to here, you will be like, this is point B, this is point C, and still this is I, this is I, this is I. So VBC will be I times R2 parallel R3, which is this one. So we have VBC to be 3.6 volt. So now we know VBC is 3.6 volt. We can calculate I2 and also I3. I3 will also calculate I3 for part C. So for I2, it is like VBC over R2. So which is 3.6 over R2 is 20. R2 is 20. So this is 0.188. And for part C, similarly, we can calculate I3, which is VBC over R3. So which is 3.6 volt over R3 is 30 ohm, which is 0.128, like this. Okay, any questions? No questions. Okay, so we move on. Okay, so next we have another resistive circuit. So we have this circuit to be a bit more complicated. So it is like we have one battery here, one battery here, one battery here, and we have 1, 2, 3, 4, 5 resistance. Yeah. So, but actually it is not so difficult, I think. Yeah. So yeah. So we have the value E1, E2, R1, R2. So R1, 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 R1. We have R2 here, and then E1, E2, E2. So the three batteries are ideal battery. Find the magnitude and direction of the current going through each of the three battery, which means we need to find I1 or minus I3 or I2. Or actually you find I1, I2, I3 is good enough. So actually here we can free to choose node analysis or mesh analysis. So maybe for this one we try to use the mesh analysis. Maybe let us define this one to be a ground node. Yeah, maybe this one to be a ground node. And we can define this one is I1. This one is I2. Just follow this this direction. So we have I2 in this direction, I1 in this direction. So I1 going through this this battery, this resistor, and this resistor. I2 going through this resistor, this battery, this resistor. So I3 will be nothing but I1 plus I2. So we have I3 equals I1 plus I2. Or you can just write the KCL here. We have I1, I2 going in this node, I3 going out of this node. So I1 I plus I2 is I3. Yeah, so so we can try to write the mesh equation. Maybe we can start from point B here. Maybe, yeah. So we have I1 R1, and then this is a voltage drop. This is this is not a voltage drop. So this is like minus E1, and then this is a voltage drop. So this is plus I1 R1, and then this is also a voltage drop, and so it is I3 times R2. I3 is I1 plus I2, so it is I1 plus I2 times R2. And then for this one, this is a voltage drop. So we have a plus E2 equals 0. Go back to the original point. So if we start from here, I1 R1 the first term, minus E1 the second term, plus I1 R1 the third term, and then plus I1 I2 all multiplied by R2 this term, and then plus E2 the last term. So this is the first mesh equation. And then for this one, we also start from point B. So we have I2 R2, I2 R1, I2 R1 for this resistance. And this is not a voltage drop, so we have a minus E2, and then this is voltage drop, so we have a plus I2 R1, and then this is voltage drop, so we have a plus I1 plus I2 all out multiplied by R2, and then this is voltage drop, so this is plus E2 equals 0. So we can slightly rearrange the term. So we have so we have the joint equation. We have this one and this one. So we have 2R1 I1, and then or maybe we can further rearrange it like and with this one R2 I1, so plus R2 all multiplied by I1. So we have 2R1 I1 here, so we have 2R1 I1, and then we have I1 R2, so we have R2 I1 here, and then the next we have I2 R2, so we have plus R2 I2 equals, move this one and this one over, so we have E1 minus E2 on the right hand side. So this is the first one, and then for the second one we have I1 here, I1 R2. So we have R2 I1 for this term. And then for I2, we have 2 I2 R1. And then we also have I2 R2. I2 R2. So we have plus 2 R1 plus R2 I2, like this. 2 R1, 2 R1 I2. And then R2 I2. So we have R2 I2 here. And then we also move these two terms over. Actually, this is E2 minus E2, so it is nothing but 0. It is nothing but 0. Yeah, so actually now we can just plug in all the values. We have R1 to be 2, R2 to be 4. So we have 2 times 2 plus 4 I1 plus R2 is 4, 4 I2 equals E1 is 3 minus 6. And then here we have R2 is 4, 4 I1 plus, yeah, still 2 times 2 plus 4 I2 equals 0. So we can slightly simplify it. We have 8 I1 plus 4 I2 equals minus 3. And then also we have 4 I1 plus 8 I2 equals 0. Sorry. And then, yeah, okay, so now we can, maybe we have I1 equals minus 2 I2. And then we can plug in here. So we have minus 16 I2 plus 4 I2 equals minus 3. So we have totally minus 12 I2 on the left side. So in this case, we have I2 equals 0.25 A. And then I1 is minus 2 I2, which means I1 is minus 0.58. So we finally can solve I1 and I2. And of course, I3 is I1 plus I2, which means it is minus 0.5 plus 0.25, which is 0.258. So this is these are the answer for I1, I2, I3. And in that case, as we know, I1 is a negative value, minus 0.58, which means that this is 0.58 going to the left side. And then I2 is positive value, which means that 0.258 going to the left side. And I3 is a negative value, which means 0.258 going upwards. And as much as you know this three current, and then you can be able to know all the no voltage. For example, suppose we have a 0 volt here, and then this is 0.58 going this way. Then you know that this no voltage is 0.5 multiplied by this R1, and then you can know this voltage. R1 is 2 ohm multiplied by 0.5, so this is 1 volt, 1 volt. And then E1 is 3, so this is 4 volt. And then in that case, 0.5 multiplied by this one, we add another 1 volt, so this is 5 volts at this node. And then E2 is 6, E2 is 6. So this node is minus 1 volt. This one is minus 1 volt. And this is, so E2 is 6 volts, so this is 6 volt. So 6 minus 1 is 1 volt, 1 volt over 4, 0.25, which match the answer. And yeah, we have 5. Yeah. And then we have a 0 volt here, -1, so we have 1 volt in this way, so 1 volt over this one, so which will be not this. So we have R1 here, so we have, this is 4 volt, so this one should be -2 volt, and in that case this is let me see, 6, 5, 1 plus 3 plus 1, and then so this is so this should be 6 volts, and then 1, 3, 5. This is 0.25, so this one should be 5.5 volt, 5.5 volt, and in that case this one is minus 0.5 volt, and in that case this is 0.258. So it should be like this. So far, any questions? So actually you can, so for mesh analysis, you can find the mesh current, and after finding the mesh current, you can find all the voltage in a short period. So here we talk about the ammeter and voltmeter. So they are two instrument or equipment. So an instrument used to measure current is called a ammeter. Use a measure current for ammeter because the SI unit for the current is the ampere, so we call ammeter. And the equipment to measure the potential difference is called voltmeter because the SI unit for the potential difference is a volt, so we call it voltmeter. And in that case, so if we try to use the ammeter, it is used to series. It should be connected seriously with the current you concern. If you try to measure this I, and then you need to connect this ammeter in series with this part, then in that case, you can measure the current going through this ammeter from point B to point A, so which is the same current as this one. And in that case, the ammeter should have a low impedance, should have a very low impedance. Otherwise, it will influence the original operation of the circuit. Just you can imagine. If you don't need to measure the current, then this part is just short circuit. This part is just short circuit. So in that case, the ammeter should have a low resistance. Low resistance. So for the voltmeter, suppose we try to measure the voltage between node C and D, which is the voltage across R1. And in that case, the voltmeter should have a high resistance. Because you don't really want to have too much current going through this path. if there are some current going through this path during your measure, then it will influence all the other current or voltage in the circuit. As much as when you try to measure the voltage or current of the circuit, you don't really want to change the operation of the circuit. The change the operation means the current or voltage across every the current going through every element or the voltage at every node. So as much as we hope the ammeter or the voltage or the voltmeter don't influence the original circuit, we hope the ammeter to have a low resistance, and I hope the voltmeter has a high resistance. Yeah. Okay, so here we talk about the RC circuit. So yesterday we talked about the RL circuit, and here we talk about the RC circuit. So it is like, suppose we have a battery here, we have a resistance, we have a capacitor here, and we have a switch here. So it originally from node B connecting S to node B, which means that this capacitance is fully discharged. At the very beginning, the capacitance is, the C is fully discharged. Which means that which means that VC is 0. VC of T is 0 for T is smaller than 0. So this means C is fully discharged, and maybe for T equals 0 second, and then the switch to point A, and then this battery will start to charge some charges to this capacitor. So if you still remember, so for the capacitance, so let me redraw the circuit here, like should be like this, RC, then this is, let me see, this is E, this is E, and I'll say this is V or VC is just a notation, it doesn't really matter, maybe I just use C here. So if you still remember, this is the current I, because this is just a single loop. And we know that VC of T equals 0 for T is smaller than 0. And if you still remember, the voltage of a capacitor is continuous, and the current of the inductor is continuous. So which means that this implies VC 0 minus is 0 volt, and as much as the voltage of a capacitance is continuous, so VC 0 plus should be equal to VC 0 minus, which is 0 volt. It doesn't necessarily be the case, but this is due to the continuous voltage of the capacitance of the capacitor. Also next, if you still remember, the relationship between the current and the voltage is like I equals C dVc dt. C dVc dt. So this is the current. Okay, so this is the voltage, and then the voltage across this resistor is like V, maybe we can say VR, which is nothing but R times I, and now we know that I is this one, which means that VR should be I times R, which is R times C dV/C dt, something like this. Okay, so now we can try to write the KVL for this loop. KVL for this loop for t is larger than 0. So we will have VR plus VC, which is RC dVC dt plus VC equals E. So this is simply the KVL for the whole loop. So VC is the voltage across the capacitance. VR is actually this one, which is IR, and we know that I is this one. So we have VR to be RC dVC dt. Okay, so this is the first order ODE, and with this initial condition. So we can change this to be RC as plus 1 equals 0. This is the characteristic equation or the auxiliary equation. So we have a S to be minus 1 over RC. And in that case, we also assume that tau is RC. So we have a tau equals RC. Or maybe you can write tau C equals RC. If you still remember yesterday, for the inductor, tau L is L over R, if you still remember. We just mentioned yesterday. So here we have a tau to be RC, so which means that S is minus 1 over tau, So for both cases, S is minus 1 over tau. Here is minus 1 over tau or tau C. But that one is 1 over tau L. So they share the same similar expression. And in that case, we know that VC, the complementary part, should be A times exponential to minus T over tau. Something like this. This is a complementary part of VC. And for the particular part, or the non-homogeneity part, which is like, this is a constant. So we will assume the particular part to be the constant, the particular solution to be a constant. And then we substitute this into the original equation. So we have this term, the first derivative of constant is 0. So we have a VCP is, so this one is B equals E. So B is E. So in that case, so the complete solution, VCT, is adding them together. So which is like E plus A exponential to minus T over tau. So we now make use of the initial condition. This is the initial condition. So we have a VC of 0 plus, which is this expression E plus A. Exponential to 0 is 1, so we have E plus A equals 0. So we have A equals minus E. And in that case, VC should be E 1 minus exponential to minus T over tau. So so this is actually this one. It just express it as RC. Actually tau is RC. And if you try to know this one, which is like I equals C dVC dt. So you take the derivative of this expression, we have a c times. This is constant, take the derivative with 0, and then take the derivative of this part will be, epsilon is a constant, so we keep it here. And then we have a minus sign, exponential to minus t over tau, or maybe I can just write it as RC, like this. And then for the chain rule, we need to take the derivative of this part, which is minus 1 over RC. So we have two negative signs, so it becomes positive. C and C will be cancelled. So it turns out to be E over R exponential to minus T over RC. So which is actually this one, which is actually the same as this one. Okay, any questions? Okay, any question? Oh, I can just write it. Yeah, just yeah. So yeah. Yeah, so for the next step, is like, so now after charging the after charging the cap to the steady state, because as you can see here, so this one, you can feel that RC is a positive value. So E to the minus to the negative value, which will be feel like if T is large. If T is large, which means that, or T tends to infinity, then E to the negative infinity will tend to 0, right? So which means that for the steady state, this one will vanish. Which means the steady state will be nothing but E times 1, which is E. So yeah, if we really write it to be VC, then it is E. Something like this, with the same shape, although the height will be different. This is the Q, but if we write it as a VC, then the height will be E. So for this case, if this is charged substantially, and then we try to turn it back to point B, then the charge will discharge to the ground. So in that case, the situation is like we have R, we have C, but it connected to the ground. So this is the situation in this case. So now we still have the similar ODE, which is like RC dVC dt plus BC, but now it only equals to 0 because we don't connect it to the E anymore. We switch it back to the point B. So which will be like this case. And now we 0 minus is like E. So for the before the switch is going back, maybe you don't really like 0. Maybe you just write a large number. It's okay, but it doesn't really matter at this moment. Yeah, but actually for this equation, it just reset the time to 0. Just like you define when you switch, it goes to the steady state at point A, and then it switches back to here at time t equals to 0. So we'll say V0 minus equals E for this case. So similarly, we don't have g of t on the right side, so which means that Vc of t is nothing but a exponential to minus t over Rc. You can just follow the calculation up to here, What you don't have is the particular solution, because for this one we have E on the right side, which is not a zero constant, which is a non-zero constant. But here we have a zero constant on the right side, so we don't have particular solution. So the complete solution is actually this one. And as much as so this should be equals to Vc0 plus, Vc0 plus, as the voltage is continuous. So now we just plug in Vc0 plus is A times 1. So as you plug in 0 here, so e to the 0th power is 1. So we have A, which is E. So in this case, Vc of t should be E exponential to minus t over Rc, which is actually this equation. So if you try to calculate this one, which is like I equals d Vc dt, c d Vc dt. So it is like c, and then take the derivative of this term. So we have e here, so we just write it here, and then we have exponential to minus t over Rc, and then we still need to take the derivative of this term due to the chain rule. So we have minus 1 over Rc. So c and c will be cancelled, so we have minus e over r exponential to minus t over Rc. So this minus sign means that as much as we define the I in this direction, as much as I is from positive to the negative, and as much as I is a negative, because this is positive, this is also positive, so the whole term will be negative, which means that the charge is discharged in this direction. The charges are discharged in this direction, going counterclockwise. So it is like going this way, the charge going this way, or the current going this way, Okay, so far any questions?